Dear students, I am Dr. Ashok Kumar Saini, Associate Professor in Mathematics in BLJS College Tosham. Today I will deliver lecture on real and complex analysis for the class BA BSc 3rd 6th semester on the topic complex function of complex variable continuity function of complex functions or functions of a complex variable. We will discuss about continuity of a complex function. A complex function w equal to f bracket z defined in the bounded closed domain D is said to be continuous This is the definition. A complex function w equal to fz defined in the bounded, first it is bounded and then bounded closed domain D is said to be continuous at a point z equal to z0 of D if given any positive number epsilon. We can find a positive number delta such that absolute value of fz minus fz naught less than epsilon whenever absolute value of z minus z naught is less than delta. Symbolically, we write limit z approach to z naught fz equal to fz naught. This means that for continuity at a point, the limiting value and the functional value at the point have the same value. A function fz is continuous in a domain D if it is continuous at every point of D. If a function is not continuous at z0, then we say that the function is discontinuous at z0, or z0 is the point of discontinuity. Remarks 1. First remark is, if fz is continuous at z0, then it can be easily shown that limit z approach to z0 fz equal to fz naught implies limit xy pair xy which we represent by z approach to x naught y naught u xy is equal to u naught. U is a function of xy equal to u naught. Limit xy approach to x naught y naught v xy equal to v naught, where fz naught is equal to u naught plus iota v naught. This adds the information that the component functions is xy and component function is u which is a function of xy and v which is function of xy are also continuous at z naught equal to x naught y naught. This adds the information that the component functions u and v are also continuous. If fz is continuous at z naught, Then component functions u and v are also continuous at z naught. First remark is this. And second remark, if the function fz is continuous, so are mod value of fz, this is also continuous. Fz bar, z bar means z bar, z is if x is equal to x plus iota y, then z bar is conjugate complex x minus iota y. And fz var whole var, it means if fz equal to u plus iota v, then fz var is equal to u minus iota v. Suppose that f and g are continuous functions at the point z naught, then the following functions are continuous at z naught. The sum fz plus gz, the difference fz minus dz, their product fz into dz, their quotient fz by dz, provided gz naught is equal to 0. Next is uniform continuity. Just like continuity we have defined in already in lower classes, we define here continuity of a function. Instead of real function, we will take continuity of a complex function. Then we define uniform continuity on the similar pattern as we defined for real function. A complex function fz is said to be uniformly continuous in the domain capital D if for a given epsilon positive it is possible to find a number delta positive. This delta depending upon epsilon only. In simple continuity, this delta depends on epsilon and the point. But in uniform continuity, this delta depending on epsilon only, not on point. So this is uniform continuity, such that the inequality absolute value of fz1 minus fz02 less than epsilon holds for every pair of points z1 z2 of the domain D, for which z1 minus z2 is less than delta. Then it should be noted that continuity at every point of an open domain D does not necessarily imply uniform continuity in D. It should be noted that continuity at every point of an open domain D does not imply uniform continuity in D. Simply we say that continuity does not imply uniform continuity. If our function fz is continuous at every point of D, closed and bounded, the condition here is closed and bounded, then it is uniformly continuous in D. If a function is continuous and in closed and bounded D, then it is also uniformly continuous. Example based on this continuity is show that the following functions are continuous everywhere in complex plane. First is fz equal to mod value of z. Second is fz equal to z bar conjugate complex. Solution here fz equal to mod value of z. Consider absolute value of fz minus fz naught is equal to absolute value of z minus absolute value of z naught. This is less than equal to z minus z naught. Absolute value of z minus z naught less than epsilon. Whenever absolute value of z minus z naught less than epsilon is equal to delta, we have put the value of mod value of z in fz and fz naught, and since mod value of z and again mod value, it simply mod value single. So this is by using the property of absolute value less than equal to mod value of z minus z naught less than epsilon. Whenever if we take epsilon equal to delta, whenever mod value of z minus z naught less than epsilon, we take it as delta. This property we have used here of absolute value, क्योंकि absolute value of a minus absolute value of b is less than equal to absolute value of a minus b. Therefore fz is continuous at z equal to z naught. Why continuous? Because condition of continuity hold here, satisfied here. Condition of to each epsilon positive there exists delta positive, such that this condition of continuity hold. Now second is fz if is equal to z bar, means z bar is your complex conjugate. Consider mod value of fz minus fz naught equal to z bar minus z naught bar is equal to absolute value of z minus z naught, because absolute value of z bar is equal to mod value of z. This is less than epsilon whenever z minus z naught less than epsilon. If we take delta as equal to epsilon, therefore fz is continuous at z equal to z naught. Next example related to continuities show that the function fz equal to 1 by z if z is not equal to 0, infinite if z equal to 0, 0 if z equal to infinity. This is the function we have defined, and we have to show is continuous in the extended complex plane. What do you mean by extended? Here we have included infinity. Here we have included infinity. Solution for z not equal to 0 or infinity, we have to find delta positive such that mod value of fz minus fz naught, fz here is given 1 by z and fz naught is 1 by z naught is less than epsilon whenever mod value of z minus z naught less than delta. This is true if we assign mod value of 1 by z minus 1 by z naught equal to mod value of z minus z naught divided by, we have taken simply LCM and solving less than epsilon and cross multiplying using and or, that is if z minus z naught less than epsilon, absolute value z minus z naught. Now restricting mod value of z minus z naught less than 1, we note that 1 divided by absolute z naught equal to 1 divided by mod value of z minus z naught into z naught plus z naught square. This is less than equal 1 divided by mod value minus mod value of z naught, mod value of z minus z naught plus mod value of z naught square, which is can be further written as is equal to 1 divided by mod value of z naught square minus we have taken z naught outside. Now we have taken z naught all square before this and negative is after this, minus, sorry for interruption because it is screen is not clear, it will clear in few. Now it is clear. Now it is clear. This the we can write it as less than 1 divided by the absolute value of z naught all square minus absolute value of z naught, and this is less than module z naught into module z naught, replace it by 1 single, less than 1 divided by the module of z naught into 1 minus module z naught. Choose delta, we now choose minimum, whichever is minimum, 1, either 1 or this denominator value module of z naught and mod value of 1 minus mod value of z naught into epsilon. It show that fz is continuous at z equal to z naught for delta equal to minimum 1 comma mod value of z naught into 1 minus mod value of z naught into epsilon. Example 8 is show that fz equal to z square is uniformly continuous in the region mod value of z less than 1. Solution is here fz equal to z square. Suppose fz equal to z square is uniformly continuous in the region mod value of z less than 1. This is given. We have to show uniform continuity. Then for uniform continuity means delta depends upon epsilon only, not on the point. Then for a given epsilon positive we can find delta positive such that mod value of fz minus fz naught is equal to mod value of z square minus z naught square less than epsilon whenever mod value of z minus z naught less than delta. According to definition we have this. Since delta depends only on epsilon and not on the particular choice of z naught, if z and z naught are any points in modulus z less than 1, then modulus z square minus z naught square, if factorize it, modulus z plus z naught modulus z minus z naught, this is less than equal to modulus z plus modulus z naught bracket closed into modulus z minus z naught less than 2 into z minus z naught. Thus, if we choose delta equal to epsilon by 2, it follows that modulus z square minus z naught square less than epsilon. This ensures that fz equal to z square is uniformly continuous in mod value of z less than 1. So, we have defined today, students, about continuity of a complex function and uniform continuity. In the next chapter we will discuss about differentiability of a complex function. You can view this online lecture on our college website www.bljscollege.com. Thank you. You are invited for any query question. Thank you.